Hello everyone. So in this video, we will talk about confidence intervals and hypothesis testing for variance, variance of a single population, and also for ratios of variances of two populations. So, um, um, well, recall what we did so far. So we said that, well, I want to infer information about the mean of a population, which is mu, and I just use x bar, okay, in order to say something about mu. We just use hypothesis testing and confidence intervals. Um, and in order to make inference about the single population, mean of single population, I just use mu. So x bar, remember, x bar is the estimator of what? Estimator of mu. Then we talk about the difference of two means, mu1 minus mu2, right? In order to infer information, to extract information from a sample, we just use x1 bar minus x2 bar, right? So, but there are two parameters here. Difference of two parameters. The estimate of difference of two parameters is x1 bar minus x2 bar. Okay? So what we do is we just make confidence intervals and hypothesis testing using these point estimators, okay, regarding mu1 and mu2. Now we will talk about a single parameter, again, of a single population, sigma square, right? Sigma square. I will try to extract information about this parameter. Just like the previous cases, in order to say something about sigma square, I will just use its point estimate, which is s square, right? So sigma square is the variance of the population, right? This is the variance of the population. And s square is this is the sample variance. It's the variance of the sample. Okay, great. So remember, I just say that, well, x bar from central limit theorem, it's normal if sigma is known. If it is not known, we just use t random variable and say that x bar minus mu divided by s over root, and that's a t distributed random variable. And similarly, we have just found the distribution of x1 bar minus x2 bar, and use that distribution to make confidence intervals and hypothesis testing. Now I will try to find a distribution, okay, distribution regarding s square. Do we know a distribution about regarding s square? Yes, in fact, so this one, x bar minus mu divided by s over root 10, well, that's something regarded to s square or s. But what I need is, but just look at this one. So this one is connected, is just connecting x bar with its estimator mu, okay? But here, so I just want to say, I want to extract information about sigma square, right? Hence, Hence, well, probably that will not work fine. So, well, let's try to see what is the corresponding distribution that we did use for confidence intervals and hypothesis testing. Well, okay, so these are the things that we have just talked about. Well, it turns out that n minus 1 times s squared divided by sigma squared. So n is something constant. That's the sample size. Sigma squared is a parameter that's a constant. But remember what s squared is. S squared is the it's a statistic, right? It's just function of the observation. So, well, this is a random variable, and this whole thing is a function of a random variable, okay? Function of a random variable, hence it's a random variable itself. And what is the distribution of this random variable? Well, we are lucky because the scientists has just worked on this for a while, and they just show that, well, the distribution of this is a chi-square random variable. That's not an x, that's a chi, okay? That's the letter chi. And I have a square over it, which is called the chi-square. random variable. Again, I have a parameter for this chi-square, which is the degrees of freedom. It has a n minus 1 degrees of freedom. So this is the distribution of chi-square. Okay, just look at this one. This is the distribution of chi-square. So what you can notice here is that, well, it's not symmetric, right? All of its values are positive. Moreover, it's not symmetric. So for x, for standard normal or t-random variable, remember we have something like this, okay? So this was the 0, right? And so it's a symmetric distribution. It was a symmetric distribution. The standard normal is a symmetric distribution. The t-random variable is a symmetric distribution. But here chi-square is not symmetric. So what is the implications of this? Well, so remember we said that if this is alpha over 2, okay, so let's write this. If this is alpha over 2, then remember what is this? This is z sub alpha over 2. Since this is a symmetric distribution, I just write here this is minus z alpha over 2, which gives an area of alpha over 2 to the left, or remember, so this leaves an area of what? 1 minus alpha over 2 to the right. So this is in fact z sub 1 minus alpha over 2, right? So in chi-square random variable, so if you just leave an area of alpha over 2 to the right, right? This is the chi-square, which leaves an area of alpha over 2 to the right. And this is the chi-square random variable, okay? Which leaves an area of 1 minus alpha plus alpha over 2, which is 1 minus alpha over 2. So this is the chi-square value, which leaves an area of 1 minus alpha over 2 to the right, or alpha over 2 to the left. So this is not equal to minus chi square alpha over 2. Okay, this is very important. Since it's not symmetric, it's no symmetry. Okay, this is no symmetry. No symmetry. Okay, so it's not symmetric, right? Hence, we should be just very careful when finding the values. So let's look at the table again. So just look at this one. Okay, so chi-square, for example, if I just want to find the chi-square value here, which leaves an area of 0.01 to the left, what does it mean? It leaves an area of, so this area will be what? This area will be 0.99, okay? So I should just go and look at the table for what? For this column, okay? So if your degrees of freedom is, for example, 10, then 2.558 is your number. What does it mean? This number is 2.558. Okay, great. Or let's pick something from here. What is this? Let's say, what is this? This is, so this is a chi-square in the middle. Let me just plot it. It's something like this. Okay, it's not symmetric. 1.689. So it's somewhere here. 1.610. So the area to the right of this is equal to what? The area to the right of this is equal to 0.90. Okay, so this area is 0.90. And what is the degrees of freedom? So this is a chi-square random variable with 5 degrees of freedom. Okay, so this is chi-square, let's say with v is equal to 5 degrees of freedom, right? Okay, great. Now, let's look at our 5-step procedure for hypothesis testing for sigma square. So the hypotheses are whether sigma is equal to some number. Okay, so this is something like sigma is equal to 5 or sigma is equal to 3. So sigma 0 just stands for a scalar, for a number. So this is also equivalent to what? H0 is sigma square is equal to sigma 0 square. So in fact, what does it? This means sigma square is equal to 25 or sigma square is equal to 9. Okay, that's exactly the same thing. H1 sigma square is not equal to sigma 0 square. Okay, so what does this mean in terms of these numbers? So these numbers, so H0, so for example, sigma square is equal to 25 versus sigma square is not equal to 25, or sigma square is equal to 9, sigma square is not equal to 9. or so sigma is equal to 5 versus sigma is not equal to 5. Okay, so they are exactly the same thing. So this is the test statistic that you would use chi square n minus 1 times s square divided by sigma 0 square. And this is my critical region. Remember, the chi-square leaves an area of alpha over 2 to the right and alpha over 2 to the left, which or 1 minus alpha over 2 to the right. Then calculate your observed value. Okay, calculate your observed value. So remember, this is your hypothesis. This is your test statistic. Sorry, this is your test statistic or what? Test statistic, which is equivalent to your random variable. Step 3 is your critical region. Step 4 is your observed random variable. Okay. And step 5, what is step 5? Just conclude. So once you have just calculated the rejection region or the critical region and the observed random value, just compare them to find whether you reject the null hypothesis or not. Okay, so step 5 is conclude. So, well, let's make an example. We have heights of 10 many students, okay? And it turns out that well, their average is 167 and their sample variance is 8.87. Okay, and the question is, sorry. Okay. So, okay, we will find the confidence interval in the next slides, but for now, please test whether sigma is equal to 6 or not, or sigma square is equal to 36 versus sigma square is not equal to 36, okay? So, well, there were 10 many students in the slide. Okay, just go back, please. 10 many students. So what does this mean? V is equal to n minus 1, 9 degrees of freedom. Okay. So I have what? I have alpha is equal to 0.05. So what does it mean? I need chi squared 0.025 and I need chi squared 0.975. Okay. So I can just find 9.75 with 9 degrees of freedom. Just go back. So here, 9 degrees of freedom, 975. What is that? It's here, 2.7. Okay, I can just find it here. And for the other value, I should just go and check the table. Okay, you can just check it at your home. So this is equal to 2.7. And you can just check it at your home, okay, at home when you're just listening the video. Well, it turns out that the value is 19.023. Okay, so you can just check it from the table. So your observed value is chi-square observed. Let's say this is observed. The chi-square observed. That's equal to, remember our definition for the chi-square random variable, n minus 1 times s square divided by sigma 0 square. That's equal to n minus 1, which is 9. S square, this is your observed s square divided by sigma 0. This one just comes from the hypothesis, okay? And it turns out that the value is 19.67, which is greater than our what? Our critical regions border. Hence, what we do is we reject H0 and say that, well, so we are just rejecting and say that, well, sigma is not equal to 6 or sigma square is not equal to 36. So remember, this is my chi-square, right? Let me just plot this. So this is 2.7 here, 2.7. And here I have what? 19.023, okay? So this is the shaded region, 0.025 here. And here, this is the shaded region. This is the, sorry, 0.025, okay? So what I found is 19.67. It's somewhere here, okay? This is 19.67. Hence, it's in the rejection region. Your chi-square observed, chi-square observed. It's in the critical region. Hence, we just reject the hypothesis. Well, the next step is finding the Okay, so now we will talk about the confidence interval for sigma square. So remember, I'm just writing the same thing. So what we write for minus z alpha over 2, the random variable z and z alpha over 2. Then we just plug in z, which was x bar minus mu divided by sigma divided by root 10. Okay, I'm just doing the same thing here. So remember, so for chi-square random variable, I have chi-square 1 minus alpha over 2 is, so the probability that your chi-square random variable is between the chi-square value, which leaves an area of 1 minus alpha over 2 to the right, or, so what does this mean? This is alpha over 2 area to the left. And this one, chi-square alpha over 2, this is equal to 1 minus alpha. Again, how? Let's plot this. So this is my chi-square, right? And this is alpha over 2. So this region is alpha over 2. And this region is again alpha over 2, alpha over 2. So the probability that your chi-square random variable is in this region, what? Is given by this, okay? Which is equal to 1 minus alpha. So what I do is I just plug in the chi-square random variable, which I have defined, n minus 1 times s squared divided by sigma squared, and just leave sigma squared alone here using some algebra. It turns out that the probability of sigma squared being between this value, which is n minus 1 s squared divided by chi-square of alpha over 2, chi-square sub alpha over 2, and n minus 1 s squared divided by chi-square of 1 minus alpha over 2. That's equal to 1 minus alpha. Hence, I can define the confidence interval as, well, if S square is the sample variance of a random sample of size n from a normal population, by the way, just like the T distribution, we need that the population should be distributed normally. Okay, otherwise you cannot use this confidence intervals and hypothesis test. So 100 times 1 minus alpha percent confidence interval. So if alpha is again 0.5, so this is 0.05, sorry. So this is a what? This is a 95% confidence interval. So it turns out that this is your confidence interval. Right? So this was a confidence interval for sigma square. How about the confidence interval for sigma? You simply just take the square root of that one, okay? So again, for the previous example, find the confidence interval for the sigma square of h of the students, okay? So we will find the confidence interval. Well, we know that S is equal to 8.87, N is equal to 10. So we just found these numbers from the previous question when we were making the hypothesis test. So this is my confidence interval, okay? Remember, this was the formula for the confidence interval, n minus 1, which is 9, times s squared, 8.87, divided by chi-square over alpha over 2, which is 19.023. Okay, let me just put it into parentheses. So this is my confidence interval. 9 times again 8.87 divided by the only difference is the chi-square random variable, okay? So it turns out that, well, look at this one, sigma is between 6, almost 6 and almost 16, okay? So sigma is almost between 6 and 16. So this is the 95% confidence interval for the standard deviation of the heights of the students in this university.